cursory examinations of data tables in the back of your Pick-em book should convince you that thermodynamic data is readily available at 25 degrees Celsius or 298.15 Kelvin. What should we do then when we need information about energy transactions for chemical reactions or other processes at different temperatures? Simply put, we use Kirchhoffs' law, which states that the standard reaction enthalpy change at a temperature T prime is equal to the standard reaction enthalpy change at a temperature T plus delta RCP standard times the temperature difference T prime minus T. The term delta RCP standard is the sum of the standard molar heat capacities at constant pressure for the products multiplied by the respective stoichiometric coefficients minus the sum of the same quantities for the reactants. Delta RCP standard is often called the standard reaction heat capacity change. Where does this equation come from? Well, we defined earlier in this chapter the molar heat capacity at constant pressure as the change in molar enthalpy of a substance with temperature. We can rewrite this equation to show that the change dH in molar enthalpy of a substance as a result of a temperature change is simply equal to the product of the substance molar heat capacity at constant pressure, CPM, by the temperature change, dT. When we integrate this equation with respect to temperature, we obtain an expression that reads the molar enthalpy of the substance at temperature T prime minus the molar enthalpy of that substance at temperature T is equal to the molar heat capacity at constant pressure times the temperature difference T prime minus T. Using this equation for all substances present either as a product or as a reactant in the reaction equation, and accounting for the necessary stoichiometric coefficients, lead to Kirchhoffs' law. Let us apply Kirchhoffs' law to the reaction between aqueous glutamate and aqueous ammonium to form aqueous glutamine and water. We know from thermodynamic tables that standard reaction enthalpy change for this reaction is equal to 21.8 kJ per mole at 298.15 Kelvin. And we would like to calculate the magnitude of delta H for this reaction at 60 degrees Celsius. We write Kirchhoffs' law as delta RH standard at 333.15 Kelvin, which is 60 degrees Celsius, equals delta RH standard at 298.15 degree Kelvin plus 333.15 Kelvin minus 298.15 Kelvin times delta RCP standard for the reaction equation. Delta RCP standard is expressed as the sum of the molar heat capacities at constant pressure for the products, aqueous glutamine and water, minus these for the reactants, glutamate and ammonium. Note that all stoichiometric coefficients in the reaction equations are 1. Extracting the molar heat capacity values at constant pressure for reactants and products from the thermodynamic data tables leads to a delta RCP standard value of 5.4 joules per mole per Kelvin. We can now plug this delta RCP standard value in the Kirchhoff equation and obtain delta RH standard at 333.15 Kelvin equals to 21.8 kilojoules per mole plus 35 Kelvin times 0.0054 kilojoules per mole per Kelvin equals 22.0 kilojoules per mole. So it appears that at least in the case just described, the heat of reaction does not vary very much with temperature. But is this a general result? or just an anomaly for this specific reaction? We will answer these questions on our next slide. Please note that when we use the delta RCP0 value, we expressed it in units of kilojoules per mole per Kelvin, since delta RH standard values are typically given in kilojoules per mole. When does Kirchhoff's law matter? Looking at Kirchhoff's law, we can easily conclude that the standard reaction enthalpy at a temperature T prime differs significantly from the standard reaction enthalpy at 298 Kelvin in three specific situations. Either the quantity delta RCP standard is very large. That would be the case when the reaction involves, for instance, the unfolding of a protein. Proteins are expected to have much larger molar heat capacities at constant pressure in the unfolded or denatured state than in the native or folded state. Another situation when Kirchhoff's law matters is when the temperature T prime is very much larger or very much lower than 298.15 Kelvin. This will rarely be realized for problems in the life sciences unless, of course, you are looking at processes taking place on the South Pole or in a thermal vent in a geyser or near a volcano. Finally, Kirchhoff's law can be shown to be important and relevant anytime we are dealing with processes where delta H of reaction at 298.15 Kelvin is very small.